I've been wanting a Commodore Pet for a while now, but so far they have been very expensive and they're quite bulky and fragile, so they are difficult to ship. The other day I saw someone selling a Commodore Pet 600 online. The seller actually showed a picture of a Pet 200 but said that the actual machine was very similar looking. This was in Gothenburg, which is within pickup distance of me, so after a pretty long discussion and some negotiation, I placed the winning bid and could secure it for a very reasonable price. And thank you for that, Per-Åke. The seller himself got it about 20 years ago when a friend of him tipped him off about a flea market where this machine was on display. Other than that, I have very little information about the origins of this machine. What I do know is that it was very likely sold in Sweden as it has been adapted for Swedish. The machine is actually in quite good condition, but it was really dirty, and I really had to make a big cleaning effort to make it presentable. I had to use a lot of isopropanol, some detergent, some serious scrubbing, and even baking soda to get it in reasonable shape. Now the color starts to approach that of the dataset. The keyboard can be detached like this, and if one removes these two screws, it can be opened at the back like this. And I must say that the inside is organized very neatly, and I think it looks great for being almost 40 years old. Originally I wanted a model 4032 or 8032, but eventually I just had to decide that a 600 was close enough. But what is a PET 600 exactly? It is actually somewhat difficult to obtain information about the PET 600. For instance, Wikipedia says nothing about the 600 or 200. Several sites that list PET versions rather comprehensively do not mention these models at all. Eventually, I encountered some 600 references. For instance, some Swede showing his PET 600 booting. But the first real clue to the origin of this machine came when I started to browse the Swedish electronics forum. So this could actually be a PET 8032 SK. Apparently SK means separate keyboard. That's what we have. 80 means 80 columns, check on that. And 32 means 32 Ks of RAM. And that could be, I don't know yet. An image search shows up a lot of round looking computers. And at closer inspection it becomes apparent that this is actually rebadged and this sticker hides something beneath. After some further digging into various computer history forums and vintage equipment sites, I encountered this statement from 2012 from a chap called Ericsson. Among all the PET CBM computers I started to rescue 6 years ago, I found a considerable amount of 8032-SK rebadged PET 200 in Sweden and Finland, and possibly also in Germany, a couple of 8096-SK rebadged PET 600, a handful 8296/D, and plenty of CBM 700. The latter were rebadged PET 700 or 700/128, which in total made a confusing business as Datatronic offered to the Swedish market one PET 600, 8096-SK.
This would mean that the PET 200 is a PET 8032-SK and the PET 600 is a PET 8096-SK. And that the PET 600 does not belong to the CBM 600 series. The CBM 610 is a CBM 2 machine which is incompatible and has a 6509 processor and is known in the US as a B128. And this is completely different from this rebadged series from Datatronic. 8096 would also imply that this machine actually has 96K of RAM, and I think it's time to validate that assumption by looking inside. The RAM is organized into these two columns, and on the right hand side we have the TI chips, and specifically those are TMS 4164-15, which each of them contains 64 kilobits of DRAM, and the total amount is then in this column 64 kilobytes. In the left hand side we have actually two surprises. One is that the maker is Inmos. For me, Inmos is not a RAM manufacturer, but the makers of the rather famous Inmos transputer. The Inmos transputer was a high-performance CPU manufactured in the 80s by a British company called Inmos, and it was supposed to be used in a matrix fashion where each node communicated in a north, south, east, west way by using high-speed serial links, 5 to 20 megabits approximately, which was a big deal and a high speed in the 80s. And there were some designs made by this, and one among those this fantastic 42 transputer design from the University of Bristol, but perhaps more famously Atari made a workstation which they called the transputer workstation, but it wasn't a great success. So for me there was a quite big surprise that they actually was a RAM manufacturer as well. So specifically this design used the IMS 2600P-15 design, which is also a 64K DRAM design, which means that both of these columns contain 64K, and that is a surprise to me because I expected this machine to only contain 96K of RAM and not 128, which questions my previous statement that this is an 8096 machine. This must be something else. After some further digging, I found another post from a guy called S.J. Gray in a discussion about these round Porsche cases. I also want to mention that these cases were patented, so you can see exactly who designed it, and if you look at the patent drawings, you will see that the keyboards are CBM2 type. These cases were designed for the CBM2 series, and only after they had failed they adapted them to the PET. The 8032 SK uses a standard 8032 motherboard, which was never designed for the SK case, so Commodore had to elevate it and rotate it to fit. This is why the IEEE connector is raised up and of the same type as the IEEE drives. There is a ribbon cable to the motherboard, same with the user port. Since the motherboard takes up so much space, they had to mount the power supply transformer to the top of the case. Now, the 8296 computer was totally redesigned and smaller, had a motherboard that fits nicely into these cases. The motherboard is narrow, leaving space on the bottom to mount the power supply. So then, that means I have to update my hypothesis. The PET 600 is not an 8096 SK, it's an 8296 SK. Let's have a look at the backside, shall we? Over here we have the rather practical reset switch, and down here we have the cassette port, and to the right hand side we actually have another cassette port, and this one has device number 2, but why one would like to have two cassette ports, I don't know. To the right of that we have the user port, and to the right of that we have an IEEE port which we can attach disk drives and whatnot, and above that we have the label for the product. Now we see that it is actually a 8296, and even mildly intelligent would have looked here in the first place perhaps. But at least we got a confirmation and now know that it actually was manufactured in West Germany. And to the right of that we do have the usual power stuff, the plug, connector and the fuse. The design of the 8296 is relatively simple and straightforward, so let's have a quick look at the key components and how they are connected. I managed to find a hand-drawn block diagram of the 8296 at zimmers.net, which is a great resource for everything related to Commodore and old computers. This computer has a 6502 processor running at 1 MHz, and it has a 16-bit address bus and an 8-bit data bus. The ROMs containing the BASIC and kernel are attached as well as the internal RAM. To the right of the RAM we have the video solution capable of generating an 80 by 25 character display, and the font is hard-coded into the character ROM. The IEEE port is served by a 6520 parallel interface adapter, and the two cassette ports and the user port are served by 6522 versatile interface adapter, and the keyboard is served by another 6520 parallel interface adapter. Let's open it up again and see if we can find this component. We find the CPU rather centrally placed, surrounded by the other circuitry, and to the right hand side we find the ROMs, upper and lower ROMs, and to the down left we have the RAM as we have seen previously, and the video solution that we find in the middle is based on the 6545 CRT controller, and the blue encircled circuit is the character ROM that is in this machine replaced to give Swedish characters. Near the IEEE port we find the 6520 that controls it, and just next to that we have the user port and the two cassette ports, and there we find the 6522 controlling them. And finally, down to the far right we have the keyboard connector, and close to that we sure find a 6520 that controls that. But now I think it's high time to switch it on. It actually starts pretty quickly, but it takes longer time for the monitor to heat up than the computer to boot. The Swedish characters are replacing 3 graphical characters, square bracket and backslash, but that's not a major problem because these are not really used in BASIC. The cursor keys are placed in an awkward position, but they are working like ordinary cursor keys on a Commodore machine, where shift is reversing the direction. In the bottom left corner of the keyboard we have the reverse key. If you hit the reverse key, all subsequently typed characters are bitmap reversed, and they don't go back to normal unless you hit shift reverse. Another peculiar key is the repeat key. Normally there are only a few keys on the keyboard that repeats automatically. It's space, it's the cursor keys, and it's the delete key. But if you hit any ordinary key it doesn't repeat unless you press repeat. Another observation that one can do is that the keypad is rather small. It lacks a column of keys here that usually contains plus, minus and enter keys. But I guess the sleek design of the keyboard didn't give room for these keys. Some of the Commodore keyboards have these special graphical characters printed on the side of the keys that can be generated by pressing Shift or Commodore. But this particular keyboard do not have these, and I started to wonder how could I generate these graphical characters in the Commodore Pet. So I thought, why not do a brute force for loop from 0 to 255 and then just print the character for each value. That should give me all the different characters that are available for the font in question. But when I did that, I encountered a couple of surprises. There were control characters in there that, for instance, generated an uppercase font, and the other surprise was that I could only move in a small window, just like on the Commodore 128. But if this would be true, I should be able to hit home twice to escape it. And sure enough, when I did, I actually went out of that, which told me that we may actually have the same type of functionality. But before we look into that, let's have a quick look at control code 14. When printed, it selects the lowercase font for the entire screen, and you can select the uppercase font as well by using the same control character but with the highest bit set. So just add 128 to 14 and you get uppercase. Let's go back to the definition of a sub-window within the screen editor. The definition of a sub-screen or a sub-window is achieved by using control code 15. By printing control code 15, the upper left part of the window is defined, and then I use a quote string and cursor key movements to move the cursor around on the screen to the point where I want to have the lower right part of the window. There I issue control code 15 again, but now with the 7th bit set. In this way I can define a window that only consists of these few lines and the scrolling is working within them. By issuing home twice I escape this. But now there must be a better way of defining this window than doing this awkward printf combination, and there is. One can use the keys Z, A and L to define the upper left part of the window, and use Shift Z, A and L to define the lower right part of the window. It works well, but it generates these ugly garbage characters because you're using ordinary keys for the shortcut. At this point there were actually two questions that bugged me that I really wanted to find the answers to. If we have a 16-bit address bus in the CPU, how can we utilize 128 Ks of RAM? It should be only able to address 64. And if we actually have 128, how come the startup screen says that we only have 31,000 bytes free? Is BASIC that horribly inefficient? In order to understand this, we need to look at the memory map of the 8032. It consists of a lower part and an upper part. The lower part is covered by a physical DRAM of 32K, and just on top of that we find the screen RAM that is covered by a specially designed VRAM of 2K. Now, if we take a look at the 8296 memory map instead, we see that the entire range from 0 to 65,536 is covered by a physical DRAM. We can also see that the screen memory is now mapped into this 64K DRAM, and there is no more a specialized video RAM. The other 64K DRAM is organized into 4 16K blocks that are mapped into the address space above 8000 hex. This expansion memory is only available if bit 7 is set in the memory expansion control register. And if it is set, bits number 2 and 3 determine which of the blocks 1, 2, 3 and 4 are actually mapped into the main memory space. If bit number 2 is cleared, then block number 1 is mapped into 8000 hex, but if it is set, block 3 is mapped into 8000 hex. Similarly, bit 3 determines which of the blocks number 2 and number 4 is mapped into C1000 hex. Even though it is difficult to exploit this expansion memory in the 8296 from BASIC 4, there is actually something that we can play with if you take a look inside the screen memory. In the 8032 we have exactly 2000 bytes that represent the 80 byte 25 characters that are displayed in screen. This goes from 8000 hex to 87CF. When looking at the 8296 we actually have 4 screens with 2000 bytes each. And these are placed at 8000, 8800, 9000 and 9800. The starting position of the screen memory can actually be configured in the 6545 CRT controller by setting the contents of control register number 12. And this is actually mapped into BASIC, so this we can experiment with. So to select screen number 2, the only thing that we need to do is to put 4 into control register 12. We are now back at the BASIC prompt, and it should be an easy matter to tell the video chip that we want to access register 12 and then put in 4 in there. But I don't want to do that just yet, because when I do I won't be able to see what I type, so therefore I will enter the restore command at the point where I will be when the first command returns. That's why I put in 0 down here. Now we can test whether it flies or not. Yes, it does. We do see screen number 2. Now let's make some more experiments here. Given that we have switched to screen number 2, let's try to copy some lines. Let's copy them from screen number 1, the one that we see now, to screen number 2, the one that we will display after the poke. And let's copy, say, 10 lines with 80 characters each. And we should poke into screen number 2, that is 34,816. And we should read from screen number 1, which is 32,768. So that's poke 34816 plus I with a value of peak 32,768 plus I. Yeah, that should do it. Anything wrong? No, let's go. Yeah, right. Now we see we duplicate the original screen, the one that BASIC knows about, into this screen number 2, when we should see our own code coming up here. Yeah, it does. Great, it works just as expected. That CRT controller was a fun little device. Let's see if we can find something more of interest in here. There's a lot of stuff here that has to do with electronics, there are timing diagrams and various tables describing the signals, minimum and maximum values and whatnot. And that is not quite what we are looking for. We are looking for the programming model and specifically the configuration registers. And I expect them to be down here. Yeah, right, here we have something. Description of internal registers. Here we have R0, R1, and let's scroll down. Great, here is the table showing all the registers, and down here we have R12, which is the register we've been using, and these 2 bits are representing the values 0, 4, 8 and 12, and these 2 bits are not used, and these 2 bits to the right here seem to indicate that we have sub-page resolution. But even further we have an R13 with 8 bits, indicating that we actually have much higher resolution in setting the start of the page down to 2 bytes. Let's try to use that. The idea here is to make a vertical scroller in BASIC by changing the start position of the screen 1 line at a time. Let's start by creating a for loop that iterates from 0 up to 6 lines, and then we call the routine that would actually offset the screen. Then we scroll back by starting at 6 and go down to 0 by using a step of -1. Call the same routine that offsets the screen, and then we just repeat that indefinitely. When it comes to the routine, we need to compute the memory address. Since the least significant bit represents 2 bytes, the memory offset is I times 40. And we mask away the upper bit to get the lower register, and we shift down the higher bits to get the high registers. This is a typical design pattern for doing this. And then we need to store the high bits in configuration register 12, like so, and then we do the same thing. We set the configuration register to 13 and store the value for the low register, and then we're finished. So this should work. This should scroll the screen up and down by 6 lines, and it does. Fantastic. Note that we have only changed the display controller's perception of where the last line of the screen is. BASIC still thinks that this is the last line and uses that for its scrolling. Time has come to wrap this up. So what did I learn by using this Commodore Pet 600? Well, for one thing, it's not a CBM 600, that's for sure. It is a 8296-SK. And it has 128 Ks of RAM. But I also learned that it has a very fine CRT controller that can be programmed and configured in many different ways. And it has inspired me to try a couple of other ideas. For instance, I think it's perfectly possible to do a pseudo bitmap implementation. And using that, it would be possible to advance the PETSCII art or ASCII art to a 2.0 level. But also it's perfectly possible, I think, to do a smooth scroller, and there is functionality in there to do a 2D space navigation system that could be used in games. And if I have enough time, it would be nice to hack BASIC to use the full 128K. But that's everything that we have today, so thanks for watching.